everyone. So my name is Fabio Sari. I'm currently a postdoc in Aichi Synchron, which is a small synchrotron in the center of Japan. So we will start with the hands-on of the GNXAS program, which Andrea explained this morning. So I will start from this figure. This I'm showing you is a scanned PDF of the red book of GNXAS, which is let's say the manual. This red book, which Andrea mentioned, and yeah, you can go to the GNXAS website, and there is you can ask for it, and Andrea will send you physical copy.
So Fabio, now you should be able to copy it. It was only permissions.
Okay.
Try to copy. I think that should work now. Okay.
Yes, okay, perfect. Thank you. Okay, so as Andrea was saying, GNXAS is actually composed of various different programs that I used in sequential order, let's say. That one output of the program is useful for the next program. So we will start with Cremol, and Cremol takes as input our structure, our starting configuration from which we will calculate the phase shifts and using Fagen. So I think okay, here for every program in this manual, all the input are detailedly described. But I think maybe it's better to see directly with using the example. So if you log into your account in the cluster, okay, I suggest you copy the GNXAS examples that are in this SView folder. So there is these GNXAS examples. Just copy to your own folder. I don't know how much you are familiar with the Combus shell, but you can do it using this command. So CP is for copy, -R is for folders, for recursive, and here you can call it whatever you like. I call it GNXAS tutorial. You can see my terminal, okay? So, okay, I will go on. I don't know.
No, we are, yeah, we can see.
Okay.
So there's no problem, yes.
Okay. So,
Fabio, just a moment. I mean,
yeah.
I'll just make some small. If anybody asks questions in between, I think it is good to interrupt and then go proceed.
Yeah, sure. Interrupt me. Feel free to interrupt me if you are behind us or if you have questions. I mean, this is an hands-on, not.
Yeah. Okay, so we'll proceed then.
So we will start with the CCL4 case that Andrea explained before. So if you just go into the folder, and you will see there are again various different folders, each for program of GNXAS. So this is not necessary, but it's easier to keep all the file separated and for each program, so that you will not be overwhelmed by the number of files. So if you go into the CRI folder, which stands for CRIMOL, already actually the program I have already run, and there are all the output present, but the input file is this ccl4.in. So if I open this, yes, okay, this is the input file for CRIMOL. So I will explain what the various input are. So first, it's a free-coded letters that can be changed. There are three possibilities: either X, Y, Z, sim for symmetry, or CRI. So this the difference is how you will tell the program the coordinates of your system. So in general, CRI will be used for crystal configuration, and or you can use symmetry, but symmetry is a bit more complicated to use, I think. And then there is XYZ that is used for when you have molecules, like in this case. So in this case, XYZ, we use XYZ, so we will give the, the real coordinates in real space. While in using CRI, that we will see in another example, we will use the fractional coordinates for our system. Then second line is just the name of the system. This is actually just for reading. And then the next one is the number of atoms that you have in our system. So this is a tetrahedral molecule with one silicon atom in the center and the 4 chlorine atom on the outside. So we have a total of 5 atoms, and then for each atom we have to give different parameters. Sorry. So first one is just consecutive number. So this is just 1, 2, 3, 4, 5. You have to follow the number of atoms, nothing particular. Then you have to give the element of your atom. So in this case, silicon. And then you give the coordinates. So in this case, okay, we already have the various coordinates. In this case, are centered around this chlorine atom. So this is a translation, but you can also use different translation. It's not important. You can also use negative coordinates. It's not a problem. Then this one is the number of neighbors. This actually it's an input that is given to the program, but is actually, you can also ask the program to calculate how many neighboring atoms you have within a given distance. Then these other two parameters, this actually it's an old parameter that is no longer used, but still remains, so you can just use 0. And then the last one is the muffin tin radius. This also you can input, you can use the number that you put here as an input, or you can tell the program to calculate it later. So if you're not sure what is the right radius, you can just put any kind of number here, it's not important, and then ask the program to calculate later. Okay. Okay, after we put all the atom, here actually should be, there are, here there are additional flags. So I will check on the manual. So these are various flags that a bit complicated. So standard choice is yes, no, yes in this input file. So these are three different flags. So the first one is, so if you want the program to search for the nearest neighbors, in general, it's always better to say yes, so that the program will calculate the right neighbors. And if you put no instead, it uses this parameter that you have written here. Otherwise, it's overwritten. Second flag is for only if we include the atoms within the first neighbor in the finite cluster, or if we want all the atom within a cutoff distance. So actually, in this case, we have a simple molecule, so all atoms are considered. It doesn't make any difference. But when you have a crystal configuration, you have you specific the coordinates of the unit cell, and then in principle you have an infinite system. And in that case, we will use a cutoff to limit the number of the initial cluster. And the second one, last one, if we want to use a single phase shift for each neutral atom, or two different phase shift depending if the photoexcited electron is near or not. This actually for GNXAS does not make much difference. So usually you can just leave yes, and so we leave yes, no, and yes. Then here we specify how to calculate the nearest neighbors. So we have to give a distance, and we also have to specify the type of atoms we want to consider as first neighbors. So in this case, we only consider one, which is silicon and chlorine, and we give a distance below 2.5 angstrom. Other flags that here you can use, it's asterisk, and in this case it means any kind of atom, not a specific element. In this case, it will not make much difference. Then this one is just This one is just 3-letter names. This is just a 3-letter names that you use for the name of the output files. So maybe I will change, so let me call it CC, just to change it to differentiate between the output files that are already present and the one that we calculate. Now then, we need to specify how many photoabsorber atoms there are in our system. So again, in this case, it's a simple case. We have our experimental data is on silicon K edge, so our photoabsorbing atom is always 1, and is this first silicon one. So we say there is only one atom, and the number of that atom is 1, because it's this one. So we have to give this number. So if silicon was in another position, you would get given different number. Then there is the tolerance for the phase shift. You can just leave this number. So one thing about GNXAS is that there are really a lot of parameters that can be changed. This is mainly due to the fact that the program was written in the 90s, and sometimes to save calculation time, you could change number of points to calculate to save time. Nowadays, it's not a problem anymore, because even on your computer, calculation is almost instantaneous, so it doesn't make much difference. Here, this number represents what type of edge you are considering. So this is in successive numbers. So 1 is for K edge, 2 is for L1 edge, 3 is for L2, and so on. So in this case, it's silicon K edge. So correct number is 1. And then here, this is the point I was telling before. It's a flag to use if we want the program to calculate the muffin tin using the normal criterion, or if we want the program to use this value that we've written here. So if we leave 0, the program will use these values. Instead, if we put 1, and I suggest we put 1, it will use the so-called normal criterion for calculate the muffin tin ratios. Okay. Then here we have to give the energy of the edge, and pay attention that this energy is actually in Rydberg, not in electron volt. So if you need to convert electron volt to Rydberg, you have to divide by 13.404, if I remember correctly. I think it's written here. Ah, 606. To convert electron volt to Rydberg. Then second one is I don't remember actually, I'm not sure. This supposed Fermi energy, but since we will use complex phase calculation, we can just leave 0 here. Then we have this is just minimum energy and maximum energy, and delta E for the for the calculation of the phase shifts. As I said before, this is to have more or less accurate calculation that then gets interpolated by GNXAS. But okay, you can leave it like this. So first number here, it gives various type of mesh. I think I don't remember all correctly. So mesh 1, it's a constant energy step. Mesh 2 is constant wave vector step, and then mesh 3 is exponential increasing energy step. So this is usually the one we use, but you can also use constant wave vector for GNXAS. So then this is the minimum energy, so starting from minus 0.2 up to 40 Rydberg, with a step of 0.1. Then here we have what type of potential you want to use for calculating the phase shift. And again, here we have various possibilities, but the one that I suggest and I basically always use the same is this leading beast complex energy dependent potential. So this way also the mean free path effects are calculated and included in the calculations. So this is selected by putting 5 here. And then second one is the gamma, so it's the the half-life of the excitation. Here you can put, if you don't have an idea, you can put just -1, and then the program will have as an internal table which have some tabulated values from previous publication, for which you will select the correct one. And if you are interested, I think maybe many of you know this. It's from this famous old paper. Then last one is okay. Actually, this is not important. It's for stereographic output of the image, but okay, we'll not use it. So we can leave like this. So I save, quit. Okay, so to run the program, so you can just write Cremol in the terminal, and then use the left arrow and the name of the input file to run it. So just like this. Okay. Yes, it's an error, but okay, this is not. This is a problem because we deleted an old part of the code, but this program, this error comes out. But okay, it's not important. So if you see here, so this is, if you remember, I changed the name of the output files for from in the input, so that now my output files have these CIC names, and the important one is this CIC.in, because this one is the input for Fagen. So if we open in this, so basically this is automatically create the input file for the Fagen code, which is the same Fagen I think that you have seen maybe yesterday in the DDS code, and so it creates automatically the cluster and how to calculate the phase shift. So okay, maybe I don't need to describe the details, but basically what it does is it calculates two different phase shifts. For this one is for silicon, because calculates the phase shifts. Yeah, for the first atom. So in this case is silicon, and it's for the excited silicon. And then the second one is for chlorine. So in this case, we only have two different phase shifts. in general, if you have two elements, you will have a free phase shift because you will have like for example, if you have a nickel iron alloy, you will have and we are calculating for the nickel K edge, you will have excited nickel phase shift, neutral nickel phase shift, and iron neutral phase shift. In this case, it's a molecule, so there is only one atom, and that atom is always the photoexcited atom. So we don't have how to say neutral silicon because there is no scattering of silicon path. Okay. So the next one that we'll run is Fagen, but before we run Fagen, we'll run GMPeak. So GMPeak is just how to say an helpful program that gives you the n-body expansion of the crystal configuration that you have done. So in this case, the input is quite simple, so we don't need to write an input file. You can just write GMPeak in the terminal. Then it will ask what is the cluster file name. So the cluster file name, you just need to give the 3 letters that we used before. So I just put C for silicon and C. Without the extension, it automatically understands what is the extension. Then epsilon is how to say a tolerance parameter to understand the 2 different paths. So how much the distance between 2 paths must be different to be different. We can use, for example, 0.1, 0.01, or you can. I think also you can put nothing and use automatic value, which I don't remember actually. I think it's 0.001, the automatic value. And then this is the cutoff, how much do you want to calculate the n-body expansion. Okay, in this case, again, it's a molecule, so the molecule is a small system, so there is no cutoff, so it's not important, you can just press return. And here, okay, finds the paths, and it has created this GNX and GMP file. So this actually contains the same information in these 2 files, but one is let's say for humans and one is for helping later in the inputs. So the human readable one is this GNP. So I will open it. And okay, here you have various information. So there actually the automatic tolerance chosen is much smaller than what I remembered. But okay, in this case, as you can see, peaks of the 2-body distribution in the cluster. Again, this is 5 atom molecules, and our photoexcited atom is only silicon. So we have only one 2-body configuration, which is the photoexcited, the excited photoelectron, goes to the chlorine atom and gets scattered back. So there is only one type of 2-body configuration, and there is also only one type of 3-body configuration, because the chlorine are in tetrahedral, so they all have the same angle. So the only possible 3-body configuration, considering that in absorption you have to start from the silicon atom and return to the silicon atom, the only 3-body path possible is sorry, the only free body configuration is silicon chlorine chlorine with 2 chlorine atoms. Okay. And here gives you the, how to say, the parameters calculated from the initial structure that you have given in Cremol. This is the degeneracy, how many how many two-body configuration of this type you have. So in this case 4, and this is the same for the free body. And in the free body also gives you this frequency. This frequency is just half of the path length. So let's say of the perimeter of this triangle. This helps you when you look at the Fourier transform of your experimental signa, because this is more or less where the signa would be in the Fourier space at half the length of the path. For two body, it's the same as the distance, so you don't need to calculate it. Okay. So we have done Cremol and we have done GMPeak. Next one, so we will do Fagen. But okay, as I said, Fagen is easy because the input file was generated by Cremol. So if we just copy, I just copy the file from Cremol, which is this CSS.in here. So I just copy the file from the previous folder to the Fagen folder. So this file here. And again, to run it, it's simply you write Fagen on the terminal, then left error for input, and you put the name of the file. And if you run, okay, it calculates the phase shift. Again, we have various output files that are called with the same name of the input file that we have chosen, and there are various ones. Important ones for GNXAS are these TL. TL contains actually the elements of the T matrix, so the phase shifts, and this S0, which instead contains the backscattering amplitude. So I don't know if you remember earlier the talk of Andrea. Basically, an XR signa is composed of an amplitude times the sign of a phase shift. Let's say this file contains the amplitude, and these files contain the phase shift. Okay. I don't know if you can follow. I'm going too fast, but if you have a question, just stop me. Otherwise, I will keep going. So, next one is actually GNXAS. So, this XAS folder. And I will open now this GNX underscore sccl.in, and this is the input file for GNXAS. So the GNXAS program is what calculates the actual XR signal for some for some two-body configuration or free-body configuration that you tell him. And these files then will be used by the last program, which is video, which is the program that actually does the fitting of the experimental data. So open this file. And first two inputs are the files created by Fagen. So this TL file and the S0 file. So yeah, I will change with the name, with the new name I selected. So here, instead of copying, you can just give the relative path. So these files were in the Fagen folder. Then here is just 3 letters for the output files. Again, I will use this different name just to differentiate. Then here we have different type of way to calculate the DER files. These are called the DER files because they do not only calculate the amplitude and the phase shifts, but they also calculate their derivatives. So that's why they are called the DER files. And the derivatives are used when doing the fitting. Let's say it's a smart way to move the structural parameter and recalculate the signal without needing to recalculate ab initio the signal. So this works if your initial guess of the structural parameter is not far from the real one, but in case it's your initial guess it's wrong, it's better to recalculate the actual signal. So the various way to calculate this are let's say 3 ways. One only calculates the total irreducible n-body configuration signals. 2 calculates the multiple scattering expansion of these signals, or 3 calculates both. So in this case we use 3. It calculates both the total the reducible n-body signal and also the multiple scattering expansion. Then the second one is just the order at which you want to stop the multiple scattering expansion. So you can go up to 8 or 6, usually it's okay. So in this case, for this second type of calculation, we calculate only up to the 6th order in multiple scattering. Okay, this is another way to minimize the multiple scattering expansion, is that you can give a cutoff in the path that the photoelectron takes, and then here, if you want to calculate derivatives or not, and we put yes, of course we want to calculate the derivatives. Then here we start to give how many two-body signal we want to calculate. So this actually can be written in a better way. So we can write it. Sorry, we can write it like this, which is more clear. So if you remember before, when you used the GMPIC, we had only one two-body configuration and one three-body configuration. And this is what we are actually given to the program. So these 3 numbers just means that we have one two-body configuration, and okay, we want to calculate. This is like a starting point and a finishing point. But in this case, we have only one signal, so all 3, it's just 1, 1, 1. Then here it's the distance of this two-body configuration, it's degeneracy, which is 4, if you remember from before. Then here it tells the program which phase shifts you want to use to calculate this linear. Now, how to know which number you want to put here? We can see in the output of the GMP program. So if we look before, we have seen this GMP, but if we look at the GNX, it gives you the same peaks in the same order, but as an input for GNXAS. So this is exactly what is copied inside the input of GNXAS. So this is the one two-body configuration, and you see here that what I showed you before is exactly the same. Then this is for 3-body, and this is for 4-body, which in this case we will not use. We just calculate for these two. So if I copy this and I open again the input of GNXAS, can just copy here, but okay, it's the same as before. Just remove this one. So this is the one two-body. So this is the one two-body. Then again we have only one 3-body. So in this case, as before, just put 1, 1, 1, and then this are the input for the 3-body, which are the two distances and the angle between them. This is the degeneracy, and then this additional parameter is if you have some permutation or something, and then the last one is which phase shifts will be used. Again, you don't need to know everything. You just you can copy from the output of GMP. And okay, last one, it's the 4-body, but yeah, I said maybe it's better not to calculate this. We will not use it, so so here we can just put 0, 1, 0. So in this case, we'll not calculate this one. So you can also remove this one. Okay. So in this case, we put 0, 1, 0 to not calculate any 4-body signal. Okay. So, okay, then additional parameter here, it's the angular momentum of the core. So this is 0 if you have basically for the excited electron from the S shell. So for K edge and for L1 edge, you have 0. Instead, if you have L2, L3 edge, in that case is from excited for the electron from 2p. So the angular momentum is 1, and so on. These other parameters are just the tolerance to cut off the calculation. You can check in the actually in the book if you want to know more, but you can just leave as it is. Yeah, GNXAS. So here this is quite detailed. Okay, you can read, but these are, how to say, various tolerance and maximum calculation parameter on L and on M and energy point, etc. You can leave it just like this. Then this is this is strange. Now here, I don't know why there is this this part. You can just leave here free. This you can just put free here. Then the next ones are the weight that I used in the output files for plotting, so it's not important. Then you can choose the K-min and K-max and delta K for plotting. So this is the weight of the X of signia. We can just leave 1. Then this is K-min, K-max and delta K. Again, we can leave like this, so maybe we can increase to 20. And then here we have to give a delta in energy to have how to say, only positive energy. So because in the initial calculation we started from minus 0.2, here we have to give a shift of 0.2. So you can leave like this. Okay. So okay. Important point, if you followed, is to change these ones, which represents the two body signia and the free body signia. Then we call GNXAS. Again, same as before, just the name of the program with the left arrow and then with the input file. And yeah, hopefully it works. Okay, so he has done all the calculations. And okay, if you look, so we have a lot of these .der files. So I called mine this new one are these SIC files, and then there is this PLO file. This PLO file should be a graphical output, but I don't know if we can see them, because I remember there was okay, so probably we cannot see them. Maybe I will show you on my laptop, because the problem is that these plot files, to plot these ones, we use quite old program that is called the Top Drawer TD, but this program has been discontinued. So now we how to say, we have the source file and we recompile it, but yeah, sometimes it has problem. And now if you connect into a cluster, maybe you cannot open Nixterm window, so it does not show, but I will show you on my PC. So hopefully you can see. Just to show you. So this GN block. Yes. So it's this. This is actually what Andrea showed you in the presentation before. These are the two body and the free body. And then instead, if we plot this, for example, G3.plot, it shows you all the multiple scattering signals of the corresponding free body. So Xi 3, 4, and 5, and so on. And here it gives you also the atomic number of the path that the photoelectron takes. So this one, and then up to the 6th order, because we calculated up to the 6th order. But you can see that already at 6th order, the signal is basically already 0, so it's sufficient. Okay. Go back to the other terminal. Yeah. Sorry that we couldn't make top drawer work, but for video, then we will use new plot, so it's okay. So okay, now we have the derivative files, and we can do the fitting of our experimental data. So the data is here in the dot folder. So if you see here, it's this CCL4.2, and if we, I think we can plot it using new plot. No. I think I cannot open the new plot. I don't know if you can or not. Maybe it's my problem because I have a Macintosh, but can you use new plot or not?
Yeah. So yes, we can use the GNU plot. I think when you gave the command, it was plot. So you go into the GNU plot and then.
Yeah, but I cannot open the window here because you see, unable to open display.
Okay, so probably then you logged into without the X client. So
yeah, okay.
So if you log into via the X client, then it will be possible to open it. But yes, we can open it. Yes. So we
Okay.
have the experimental data. Yes.
Okay, let me maybe wait, maybe. Maybe this way will work. Okay, now no error, but maybe it's slow. Yeah, it's slow because I'm in Japan, so it takes time to arrive here. Okay, but okay, you can see here this is the. Okay, I will not move it much. The experimental data of silicon KH, and this is what we. So in GNXAS, this is actually the data that is used as fitting. You don't need to do any extraction and then fitting. We just use the raw experimental data as the input file. So this is what will be used. Okay. So if you go to the fit folder, so this stands for video, which is the fitting program. And the input file is called fit cln.in. Okay. And okay. So first one, so this program actually used some libraries, so-called CERN libraries that were developed by CERN for, how to say, for minimization procedure and so on. It's also quite old, so it's I think, I don't know if there is still a manual somewhere, but any case, point is, the first thing that we have to give to the program is this table of parameters that we want to fit. So every time we need some new parameter, we have to add it here in this initial table. And important point is that this table is, how to say, numbers should be aligned every 10 characters. So we should follow this, how to say, this arrangement. This is important. Then as far as the contents, the first column is just a number. So you can put any number, you don't need to start from one. So it's not necessary. The second column is just name for the parameter. This is just for you to remember what is this parameter. So for example, this is R1 is just the distance between the silicon and the chlorine. Third column is the initial guess, initial value that you can use. Fourth column is the how to say, the step that we want to use to search for this parameter. So how much should the program move to find the minimum? And then last two columns is just the range. How much can we move? So now I will skip for now this one, and I will talk more about them as when we encounter them in the input. Then after that, we should leave one blank line here. This is also important. And then we start for the various input in the program. First one is how many experimental file we have. So in this case, only one. So just put one. But as Andrea mentioned, we can also analyze simultaneously different experimental files. And this is useful when you have, for example, an alloy. So again, if you think about nickel iron alloy, for example, you will have a neighboring distance between nickel and iron, and if you measure the K edge of iron and the K edge of nickel, you will see the neighbors of this distance neighbor between a nickel and an iron atom in both edges. And if you fit them simultaneously, you can only use one parameter to fit both of them, both in the K edge of the nickel and in the K edge spectra of the iron. So you can reduce the number of parameters and use the same to have a global minimum, let's say, instead of fitting one edge and then another edge, and maybe the value that you obtain is slightly different. Okay. Then you have a name for the output file. Again, I will use the same as before, but this you can use 3 letters that you want, but it's important that it's 3 letters. This is the energy range for the pre-edge. I don't have much time left before lunch, so maybe I will go a bit faster this time. So this is the energy range for the pre-edge, to do a linear fitting on the pre-edge. Then this is the maximum energy for which we calculate the edge energy. And in GNXAS, or more precisely in video, we consider the energy edge as the point where the derivative of the absorption with respect to the energy is maximum. This is different from other ways of taking the edge energy. Usually people consider when the energy is half of the jump. Another possibility is that you give the energy edge. To do that, you have to give here, if you put here 0, then you can put the energy that you want as edge here. But okay, in this case, we'll let it's better to let the program search for it. So for up to 2000 electron volt, we'll search for the energy edge. Then here, this is for the mesh of delta K. If we want it constant, you can put yes or no. Okay, leave just no for now. Then this is how many background splines we want. So this is for the post edge, so for the XF signa, how many intervals of fitting we want for the background. In this case we use only one, so here we put 1, then we put the energy range of this region, and then the degree of the polynomial for this background. So in this case we use a 4th order polynomial. Here, this is for double electron excitation, as Andrea told you. So here we say yes, we want, we have one double electron excitation, and there are various shapes that you can use to fit this double electron excitation. This is one of them, E. I think that, again, this is explained in the book. Yeah, so this is actually the function for the double electron excitation. So this is A is for arctangent like, A is for, this is, I think, hydrogen-like background. And then there are other shapes, Lorentzian and so on. You can choose, but all of them have 3 parameters. Have 3 parameters, which are just these 7, 8, and 10. And these numbers are actually the numbers of this table. So these 7, 8, 10 are these 3 parameters, which are the energy at which the double electron excitation is present, and then the jump, so how much is the height of this double electron excitation, and the delta E, so how much it's the broadening of this double electron excitation. So whatever shape you use, there are these 3 parameters that can be fitted also. Then we have, these are regions of energy that are not considered in the fitting. This is useful, for example, when you have a glitch in your data. You can just put the energy points that have a glitch in them, and then they are not considered in the fit. So you don't need to, to modify your experimental data, but you can just put this in the input of video. Then here we have the weight at which you want to fit. So this is 1. Second one, you can just leave 0. Okay, I will keep fast because I don't have much time, but maybe in the afternoon I will explain. Sorry, better when we see another example. So these are just, I think, output for graphical option. Then this is the mean free path, but because we used the complex potential, we can just leave 0. These 14 and 13 are this experimental resolution and gamma. Again, because we use the complex potential, gamma we can just leave 0, and the experimental resolution is the half width energy resolution of your experimental data. So this depends on where you take the where you take the data. Okay, so I think I will stop here, and then we will continue in the afternoon. So because then next parameters are the most important ones. So we'll continue later. Yeah. And for now, if you have any questions or things or comments, are welcome.
First and foremost, thank you, Fabio, for describing the input files and the details for the hands-on session. So thank you so much.
Thank you.
So the session is open for questions. If you have any, so please feel free to ask them. Could you please come down? It will be...
Hello, do you hear me?
Yeah.
Okay. So in one input file, there is like the total contribution for the KH, it's 1. So I just wonder that if you want to like calculate the contribution for the grazing angle and the normal angle separately, so can we do it here?
No. Right now, that is not possible. I think it only calculates the total ones. So I think this. So actually, this I think depends on the Fagen, and in this case, our Fagen calculates only the average, polarized average signal, phase shifts, and so on.
Okay.
So it's only the total one.
Yeah.
But maybe if you use another, I don't know, version of Fagen that can calculate only for a given angle, then I think, GNXAS can, you can use the output of Fagen and use it as input of GNXAS. But as far as I know, we didn't try this one.
Okay.
But it could be something to think about. So thank you.
Okay. Yeah, most welcome. And another question, it's very basic.
Yeah.
It's concerning the structure file.
Yeah.
So this is very simple system. So for example, if we go for some complex system, so is it possible like to use some program and convert the CIF file to your input file, or we can just copy the atomic positions means in the general input?
There was a way to generate the input file using a CIF file, but I don't know if it's still available. I have to check. But anyway, for Crystal, you can use, basically you can just put the input, the unit cell using another option, which is changing in the Kreml the first parameter. Instead of XYZ that you use, we put Cre for crystal configuration. Now you just put the unit cell of that system that you want to study.
Yeah.
So for conversion, I don't know, you can use like Vesta or this kind of program. Then read the GIF file and then extract just the fractional coordinate of the unit cell.
Just one question. Which program did you mean?
Kreml.
Okay. Otherwise, just a comment, sorry. Salim, there is the Babel program that you can download, and that basically converts any structural file in any other structural file.
Okay. Yeah, I don't know. I think there are many programs that do this. I use usually Vesta. I think it's another one that is. So what you do is you read the GIF file, and then you just export the fractional coordinate of your unit cell.
Okay. So here.
So in the afternoon, maybe we will see the the germanium case. In that case, it's a solid system. So.
Yeah. Okay. Thank you. Thanks.
Okay. Thank you.
So, any more questions?
Just a question about the schedule.
Okay, so I don't think if that's the case, let us thank the speaker and thank you so much. So
Okay, see you later.
Yeah. So we will meet again at 4 in the evening.
Yeah, which is at my
Okay, sorry. It
9
will be
o'clock.
at 2.
No, it's at
No. It will be at 2.
schedule, but normally because it finishes at 5. So today is different from the other days. So we meet at lower down the window so that we see the schedule.
Yeah, sure. Sorry.
Yeah, could you show the program again, Fabio?
Wait. Okay, I think you can see it, right?
Yeah. So you see, we start at 2 because of the time difference with Japan. We have to change a little bit the program. So in between here, there will be, as usual, a 30-minute break.
Yeah. So it's here actually it's up to 3.5.
Yeah,
Then
that's right. 3.5.
then there is a 30 minutes break, and then start again at 4. Okay.
So then see you all at 2. So in afternoon.
Okay.